Good morning, students, and a very warm welcome to the fifth lecture of the course MA 101 Calculus and ODE. In today's lecture, we will discuss the ratio test and the Nth root test for the series of non-negative terms. This is section 8.6 from the book Calculus and Analytic Geometry by Thomas and Finnis. So far, if given a series of non-negative terms, we have discussed the integral test and the comparison test. These are called extrinsic tests, right? So, extrinsic tests, the tests that depend upon comparing series with integrals or other series. These are called extrinsic tests. They are useful, but for many reasons, we should look for the tests which do not require any comparison. As a practical matter, we may not be able to find the series or functions we need to make a comparison work, right? Also, in principle, the information about a given series should be contained in its own terms, right? Their terms should give the behavior of that series. So that's why now we're going to discuss the intrinsic test, the test that depend only on the series at hand, right? So looking at the series only, the terms of the series, we gonna decide the behavior of that series, right? So we have two intrinsic tests. First is the ratio test. Second is the Nth root test. See the ratio test. Ratio test measures the rate of growth or decline of a series. The rate of growth means how the terms are growing or declining by examining the ratio of two consecutive terms an plus 1 by an. Right? Now, for a special case, suppose if the series is a geometric series. If it is a geometric series, then nth term is an plus 1 by an is a into r raised to the power n plus 1 upon a into r raised to the power n, which is equal to r. And r is the common ratio, which is a constant, right? So for a geometric series, the rate at which terms are growing, right? The rate of growth is a constant, right? And the series converges if and only if its common ratio mod of r is less than 1. This is what we have discussed so far, right? Now we're going to define what ratio test is exactly. The ratio test, let summation an be a series with positive terms. So we are assuming that each an is greater than 0. And suppose that their ratio, limit of this ratio is equal to a number rho, right? Now depending upon what this rho is, we can decide that what is the behavior of this series an, right? The series converges if this rho is less than 1. If limit n tending to infinity, an plus 1 by an is a number rho which is less than 1, it means the series is converging. And if this rho is greater than 1 or if it is infinity, then the series diverges. These are the two results. The third case, when rho turns out to be equal to 1, when their ratio, limit of their ratio is equal to 1, then this test is inconclusive. We won't be able to conclude anything from ratio test. We need to look for some other test in that case. Right? So let's apply this test. The only thing you need to remember is find the ratio an plus 1 by an, take their limit. Their limit is some number rho. Depending upon if rho is less than 1 or greater than 1, you can decide that the series converges and diverges respectively. And for the case when rho is equal to 1, why the test is inconclusive, let's see with a couple of examples. Consider rho is equal to 1. Then the following examples show that some other test for convergence must be used. Now see this series. These both are P series, right? And we know P series converges when P is greater than 1 and it diverges when P is less than equal to 1. Now see here, P is equal to 1, so this series diverges, and for P is equal to 2, this series converges. This we have directly written from the P test, but now see what happens if we apply ratio test over here. So this series an plus 1 by an is equal to 1 upon n plus 1 upon 1 by n, which turns out to be n upon n plus 1, and as n tends to infinity, this will tend to 1. Right? So you can write it as 1 upon 1 plus 1 by n, and then you take limit n tending to infinity, this will turn out to be 0, you have 1 as the limit. So though this number turns out to be 1. For this series, summation n going from 1 to infinity, 1 upon n square. Check the ratio of two consecutive terms, an plus 1 by an is equal to 1 upon n plus 1 whole square upon 1 by n square, which turns out to be n upon n plus 1 whole square. So this is also going to 1, tending to 1 as n tends to infinity. Right? So what we can conclude from here that in both the cases rho is equal to 1, yet the one series is diverging and the other is converging. Means whenever you have this number rho is equal to 1, the ratio test is not able to conclude the behavior of the series. That's why we say that whenever rho is equal to 1, the test is inconclusive. See this example. Applying the ratio test, investigate the convergence of the following series. The series is summation n going from 0 to infinity 2 to the power n plus 5 upon 3 to the power n. So the nth term of the series is 2 to the power n plus 5 upon 3 to the power n. To apply ratio test, you need to find the limit n tending to infinity an plus 1 by an. So an is here, write what is an plus 1. An plus 1 is 2 to the power n plus 1, just replace n with n plus 1, plus 5 upon 3 to the power n plus 1. Now you look at this ratio an plus 1 by an. So this is an plus 1 divided by an. So this term cancels out. We have 1 by 3 here coming from here. Then this term as it is in the numerator and in the denominator. Now divide this whole thing by 2 to the power n and this thing by 2 to the power n. So you have 2 plus 5 into 2 to the power minus n upon 1 plus 5 into 2 to the power minus n. Now when you take the limit of this one as n tends to infinity, this whole term, this will tend to 0, this will tend to 0, and this limit of this one is 1 by 3 into 2 by 1. So 2 by 3 is the value of rho. Right? When you take limit as n tends to infinity, this turns out to be 2 by 3, and since this rho 2 by 3 is less than 1, by ratio test we conclude that the series converges. One point to notice here is that rho has nothing to do with the sum of the series. Rho is not the sum of the series. Right? Rho is a number which tells you the behavior of the series. This doesn't mean that sum of the series is 3 by 3. You can actually find the sum of the series if you're interested. Write it as summation 2 by 3 raised to the power n, that is one geometric series, plus 5 upon 3 raised to the power n, another geometric series. Find the sum of two geometric series, and that will turn out to be 21 by 2, this you can do. Next is applying the ratio test. Investigate the convergence of the following series. summation n going from 1 to infinity 2n factorial upon n factorial into n factorial. So the nth term of the series is given by an. Find an plus 1 just by replacing n with n plus 1. So we have 2n plus 2 factorial upon n plus 1 factorial, n plus 1 factorial. Now look at this ratio an plus 1 by an. So when you write n plus 1 by an, write 2n plus 2 factorial as 2n plus 2 into 2n plus 1 into 2n factorial, so that this 2n factorial cancels out. So this 2n factorial cancels out with 2n factorial. This n factorial cancels out with these one. You have n plus 1 in the denominator, and in the numerator you have 2n plus 2 into 2n plus 1. This n plus 1 also cancels out with this one. You will have a 2 outside. So this is 4n plus 2 upon n plus 1. Now when you take the limit of this ratio as n tends to infinity, this will turn out to be 4. So your rho is equal to 4 and this rho is greater than 1. So we conclude that the series diverges by the ratio test. The next example. Here again we have to investigate the convergence of the series, where series is 4 to the power n factorial into n factorial upon 2n factorial, summation n going from 1 to infinity. So this is our an. Find an plus 1, just replace n with n plus 1 here, here and here. So you have an plus 1. Now look at this ratio an plus 1 by an. Now when you write this ratio, just here when you have 2n plus 2 factorial, open this 2n plus 2 factorial this way, right? So that here 2n factorial is there in an, these two terms cancels out, right? Here you have 4 raised to the power n plus 1, 4 raised to the power n, this cancels out, you will be left with only 1 4. Here n plus 1 factorial cancels out with n factorial, leaving n plus 1 into n plus 1. So you have 4 times of n plus 1 whole square upon 2n plus 2 into 2n plus 1. This also cancels out. 2 outside, this cancels out. So you have 2 here. So this is 2n plus 2 upon 2n plus 1. And when you take the limit of this one as n tends to infinity, this tends to 1. So we say that rho turns out to be equal to 1. So we say that the ratio test is inconclusive. We won't be able to conclude anything from ratio test. So we need to figure out that we have to look for some other test, or we have to just look at the terms of the series so that we can conclude something about it, right? But from here, what you can conclude from here is an plus 1 upon an is equal to 2n plus 2 upon 2n plus 1. So we can write an plus 1 is equal to 2n plus 2 upon 2n plus 1 multiplied by an. Right? See this one. We have noticed that an plus 1 by an is this one. Right? So we can say an plus 1 is equal to 2n plus 2 upon 2n plus 1 times an for every n we are talking about, right? Now this is a number which is greater than or equal to 1, right? Because here you have 2n plus 2, here you have 2n plus 1. When you divide these two, you will have 1 point something, right? So from this expression, we can conclude that whatever an will be, an plus 1 will be, it should be greater than or equal to an for all values of n. We do not know exactly how much greater, but we can conclude that an plus 1 is going to be a number greater than or equal to an because of this expression, right? And we knew how an is given. An was given this way. So when you substitute n is equal to 1 here, so you have 4 times 4 divided by 2 factorial, a1 is 2. And from this conclusion, we can write that a2 is going to be greater than or equal to a1, right? And a3 is going to be greater than or equal to a2. So we can say that a1 is equal to 2 and A1 is less than equal to A2, which is less than equal to A3, and keep on going like this, right? Therefore, all the terms of the series are greater than or equal to 2, right? First term of the series is 2, next is bigger, next is even bigger, and nth term. So we can say that the nth term is going to be bigger and bigger, so it does not approach 0 as n tends to infinity, because the first term is 2, next term is something bigger, next is something bigger. So there is no way that the limit of an as n tends to infinity will go to a number 0. So we can say that the nth term does not approach 0. An does not approach 0 as n tends to infinity. This is what we have concluded from here. Now after this, what we can conclude? You remember this theorem which says that if this series converges, if summation n going from 1 to infinity an converges, then nth term will tend to 0, right? And what will be the negation of this one? If nth term of the series does not tend to 0, then the series cannot converge, right? If this series converges, nth term has to tend to 0. Now here, since the nth term is not tending to 0, it means the series should not be converging. So we can conclude that the series diverges. Because if the series would have been a converging series, then the nth term would have tended to 0. Right? So we conclude the divergence. Let me repeat one more time. This is the problem given. The question is applying the ratio test, investigate the convergence. So we have tried applying the ratio test, find out what is an plus 1 from an, then take their ratio, then find their limit, but it turns out to be 1, right? So the test basically is inconclusive. Since it is said that apply the test, we have applied the test, but the test turns out to be inconclusive. Then still we want to investigate the convergence of the series. Now look at the terms of the series. While applying ratio test, we have this relation that an plus 1 by an is this number. Now this number is a number greater than or equal to 1, which means that an plus 1 is going to be a number greater than or equal to an. It means that if a1 from here, a1 is 2, a2 is going to be a number bigger than 2. Then a3 is going to be a number bigger than a2. So these keep on increasing, right? So we can say that each term of the series is a number greater than 2, and we can conclude that the nth term is not going to approach 0 as n tends to infinity, right? Because it keeps on increasing. And we have this result which says that if a series converges, the nth term will tend to 0 as n tends to infinity, right? So the negation of this would be if nth term is not tending to 0, then the series cannot converge. So here the nth term is not tending to 0, so the series cannot converge, or we can say that the series diverges. Next is the nth root test. So the convergence test that we have done so far for this series work best when the formula for summation an is relatively simple, right? Now we consider this example and we try to apply all the tests that we have done so far. Let an is equal to n by 2 to the power n when n is odd and 1 upon 2 to the power n when n is even. The question is, does the series converge? So we'll try to apply all the results that we have done so far. First we'll write the first few terms of the series. So when n is equal to 1, it is odd, so it is 1 by 2. Then n is equal to 2, 1 by 2 square. When n is equal to 3, coming from here, 3 upon 2 to the power 3. When n is equal to 4, 1 by 2 to the power 4, and we write some terms. Now look at these terms, clearly they are not forming a geometric series, so we cannot apply that formula over here. So we cannot apply geometric series. Next, we try to apply the nth term test for divergence, with the help of which we can conclude the divergence of a series. Then the nth term test for divergence says that if limit n tending to infinity, limit of an as n tending to infinity, if this is either this does not exist, or if this is some number different from 0, then we can conclude the divergence of the series. Now you take the limit as n tends to infinity. Now this will tend to 0. As n tends to infinity, an tends to 0. So we cannot conclude anything from the nth term test for divergence also, right? The next test is the integral test. Now to apply integral test, we must look for a function such that f of n, this a of n is nothing but f of n for all n. The function must satisfy some conditions, that it should be decreasing, positive and continuous. So the integral test also doesn't look promising here, because that for n is equal to odd and n is equal to even, you have different values. The function must be taking different values, right? Next is the ratio test, which we just did. Let's apply ratio test. So look for this ratio an plus 1 by an. So when you look for an plus 1 by an, this will turn out to be 1 by 2n when n is odd, and n plus 1 by 2 when n is. Let's see that how this an plus 1 by an turns out to be this one. Now we are given what is an, right? Now based on this an, try to write an plus 1. Replace n with n plus 1. So an plus 1 is equal to n plus 1 upon 2 to the power n plus 1. Now when n plus 1 is odd, right? Likewise, an plus 1 when n is even. When n is even, n plus 1 here, 1 upon 2 to the power n plus 1, when n plus 1 is even. This is an plus 1. Okay. Now you see this ratio an plus 1 by an. Now when you find out the ratio an plus 1 by an, first case we consider when n is odd. When n is odd and you find an plus 1, so you have to take n plus 1 as even. So an plus 1 comes from here, and when n is odd, an comes from here. So an plus 1 by an. When n is odd, n plus 1 is even. So you take an plus 1 from here, and n is odd, an from here. When n is even, in that case, an plus 1. N plus 1 will be odd. So an plus 1 comes from here, and an comes from here. Now when you divide them, so an plus 1 by an, this cancels out. So you have 1 by 2, and here also in the denominator you have n. So this is 1 by 2n. And here this 2 to the power n, 2 to the power n cancels out. So you have n plus 1 by 2 when n is even. Right? So this is the ratio an plus 1 by an. Now when you take the limit as n tends to infinity, so you see in this limit, here when n is odd, 2n is in the denominator. When n is even, in the numerator you have n. So the ratio is alternately small and large depending upon n is odd or n is even. So we could not be able to find the limit. So this limit n tending to infinity an plus 1 by an, this ratio has no limit. So we cannot conclude anything from the ratio test. So we need a test that will answer this question whether the series converges or diverges. That is the nth root test. Now we'll define what is nth root test. The nth root test says that let summation an be a series with an greater than equals to 0 for n greater than equals to capital N. Means the ratio test allows us that the first few terms could be negative, but after a stage an is going to be greater than or equal to 0. And suppose that limit n tending to infinity nth root of an. So we are finding nth root of an, and this turns out to be number rho. Now depending upon this rho, we're going to conclude the behavior of the series. The series converges if rho is less than 1 and diverges when rho is greater than 1 or is infinite, and again the test is inconclusive when rho is equal to 1. Okay. Just like the ratio test, in ratio test we were looking for the ratio of two consecutive terms. In nth root test, we are finding the nth root of the nth term and calling that as a rho. Now let's apply nth root test on this example which we were working on. So this is our an. To apply the nth root test, to find 1 by n of this one. So this is nth root of n divided by 2 when n is odd, and 1 by 2 when n is even. So no problem, we have an raised to the power 1 by n. So now when you take limit as n tends to infinity, so when n is even, we are getting 1 by 2. No problem. When n is odd, we have to take the limit of this one. So limit of this quantity. Since n to the power 1 by n tends to 1 as n tends to infinity. When you take limit n tending to infinity, the limit of this number, this quantity is equal to 1. So we can say that the limit of an to the power 1 by n when n is odd, it is also equal to 1 by 2. Right? So we conclude that limit of this is equal to 1 by 2. So by nth root test, the series converges because rho is 1 by 2, which is less than 1. Right? So see next example. Applying the root test, which of the following series converges and which diverges? So the first series, summation n going from 1 to infinity, n square by 2 to the power n. So this is an is equal to n square upon 2 to the power n, right? So you find the nth root of this one. So the nth root of this one is nth root of 2 to the power n is 2, and nth root of n square we can write it as nth root of n whole square, and this tends to 1 as n tends to infinity. So 1 square, basically 1 by 2, which is less than 1, and hence the series converges by nth root test. See here it is already written applying the root test. So that's why you are applying root test. Not every time it is written that use this test to find the convergence of the series. So in that case you have to look at the terms of the series. The term has 2 to the power n square. So it's easy to go for nth root. But if you have factorial in the nth term, then we generally apply ratio test. See next. Summation n going from 1 to infinity 2 to the power n by n square, just reciprocal of this one. The nth term is reciprocal of the nth term of this series. So the nth term is 2 to the power n by n square. Taking nth root of this one is 2 upon nth root of n whole square. So when you take the limit, this tends to 1. So this is 2 by 1, which is greater than 1, and hence we can conclude the divergence by nth root test. That's it. Have a nice day.